Hello everyone, my name is Ziping Lu from Electrical Engineering Department at the University of Washington. Today I'm presenting my research on submodular optimization for voltage control in power systems. So power systems are large-scale interconnected networked systems consisting of many units, including generators, transmission lines, and loads. And power system stability is the ability of power system to regain a state of operating equilibrium after a disturbance. So power system stability has many subclasses, including voltage stability and generator rotor angle stability. Today, we focus on the voltage stability problems. So voltage stability in power system refers to the ability of power system to maintain voltages of every bus within desired limits. It has two cases. One is when the power system is under normal condition. Every bus should have voltage within the range. And another case is when the power system has a disturbance. Then the voltage may drop below the lower bound temporarily, but if the voltage can go back to the region, then it's still stable. Otherwise, the voltage may drop uncontrollably and cause voltage collapse. Voltage instability and voltage collapse has caused many blackouts in history. For example, in 2003, North America had voltage instability started from northern Ohio. As a result, 55 million people lost power for many days, with a huge economic cost. Similarly, in Tokyo and Sweden, voltage collapse also happened and caused many blackouts. Given this serious consequence, the question we really want to address is, how does the power system control voltage? Okay. So the voltage at each bus is closely associated with its power. Typically follows a curve on right-hand side corner. The power we know demanded by a load has two components: the real power and the reactive power. And the voltage is closely related to the reactive power. The voltage deviates from a desired value typically when the reactive power supplied by the generator cannot meet the demand at the load. When the voltage deviations occur, what we can do is to add a capacitor bank at this load. And the reactive power can be injected from the capacitor bank to pump up its voltage. On the figure, we can see that after we add the capacitor bank, the operating point will move away from the collapse point to a steady state. However, so some people may think that when the low voltage occurs, we can simply add a capacitor bank at this problem bus. However, it's not so easy because the reactive power injected at one bus may impact many neighboring buses. For example, in the first figure, the bus 1 has low voltage. And if we simply add the capacitor bank at bus 1, what happens is, in next figure, the voltage at bus 1 is fixed. However, this power flows to its neighbors, especially in bus 2. The voltage now at bus 2 goes above its upper bound and hence cause a high voltage problem. In this case, a better solution may be in figure 3, when we add a capacitor bank at a bus, not at bus 1 and 2, but it's a bus near to bus 1 and 2. As a result, this power will split and flows to 1 and 2. As a result, bus 1 has voltage at desired level, and bus 2's voltage does not exceed its upper bound. So a key question we address in this project is where to inject direct power to fix the voltage problem when a lot of buses have voltage lower than the lower bound. This demo shows how our method works on the IEEE 300 bus system. It has two important files. The main file, it generates the states also around our algorithm. So every operating point is calculated by met power based on the default data. Okay, so if we run the first section in main file, it creates a steady state that no voltage problem occurs. So you can see at a steady state, currently there's no bus has a voltage below the lower bound, and no bus have high voltage beyond the upper bound. Also, we can see the result in another file called plot figures. If you run the first section, it generates a figure of all voltage deviations at all buses. Currently, at steady state, there is no bus has a voltage problem. Okay, then we go to the next. If you continue to run it, the user can manipulate the load level to create scenarios that have low voltage problems. Okay, it asks the user to input a number between 1.04 to 1.08. For example, if we choose 1.06, basically it means we increase the demand at all buses by 6%. So now you can see after calculation, the system says there are 11 buses that have low voltage right now, and no bus have high voltage. So if we go to the plot, we can and run the second section, we can see, okay, currently a lot of buses have low voltage, and you can know where the low voltage occurs. Then we go back to our main file and run the last section. So now our submodular method begins to work. It selects which bus to inject direct power such that the low voltage problem can be fixed. So the submodular algorithm works in the following. It first formulates a cost function that can capture both the switching cost and the predicted voltage deviation after control. And in each iteration, it greedily selects a bus that by injecting direct power there, it can lower the cost most. Okay, now we get a result. So 11 buses having low voltage before, and it selects 5 buses to inject direct power. These 5 buses are different from those having low voltage. Okay, we can observe that the deviation after our submodular control is lowered a lot. Initially, the deviation is over 100, and now it's lowered to 16 with only 5 switching cost. If we go to plot to see the last section, you run the last section, we can see the voltage deviation after our submodular control. So every bus having low voltage now goes back to its normal region, and it shows this submodular control works very well. Okay, I think this is all from my demonstration. Thank you.